This is a video from section 9.5. Recall, a first-order linear differential equation can be written in the form y prime plus p of xy equals q of x. So we're going to take a look at some examples. The directions say to solve the initial value problem. So we're going to go ahead and take a look at example 1. Suppose I had xy prime plus y equals 3x squared. And my initial condition is y of 1 equals 4. I'm going to show you where that initial condition comes in a little bit. But we're going to solve this first-order linear differential equation in much the same way we did in the previous video. And so what we want to do is the following. We want to divide both sides by x. And so y prime plus 1 over xy is 3x squared divided by x. And so y prime plus 1 over xy is equal to 3x. So in this problem, notice that p of x is equal to 1 over x. And so my integrating factor is I of x is e raised to the integral of 1 over x dx. But this is equal to e to the natural log of x, which is equal to x. And so I'm going to multiply both sides by x. And so we get x times y prime plus 1 over xy. That's on the left side. On the right side, we get 3x times x. So x y prime plus, now x times 1 over x is equal to 1, right? And so we're going to add y, and then we're going to set that equal to 3x squared. And if you don't mind, I'm going to write this as xy prime plus 1y equal to 3x squared. And I want you to notice something. Notice how the derivative of y is y prime, and the derivative of x is equal to 1. Again, I'm talking with respect to x, right? So I could write this as the derivative of x times y. And I'm going to set that equal to 3x squared. So xy is the integral of 3x squared dx. And so xy is x cubed plus c. Now, let's go ahead and write that on the other side. So xy is equal to x cubed plus c. But remember that y of 1 is equal to 4. So we're going to look for a particular solution to this differential equation. Now, when I say y of 1 equals 4, what that means is when x is 1, y has to be equal to 4. So we could use that to solve for c. So 1 times 4 is equal to 1 to the third plus c. So 4 is equal to 1 plus c, so c is 3. And what that says is xy is equal to x cubed plus 3. And if I solve for y, I get y equals x squared plus 3 over x. And that would be the solution to example 1. Let's take a look at example 2. Suppose I had the following. T cubed times dy dt plus 3t squared y is equal to cosine of t. and y of pi equals 0. So again, I'll show you where this initial condition comes in momentarily. Now, we can go through the integrating factor just like in the first example, but I want you to notice something. Notice how the derivative of t cubed is 3t squared, and the derivative of y is dy dt. And so what that means is I could write this as t cubed y, and then I'm going to take the derivative of that, right? And this is equal to cosine of t. But what that says is t cubed y is equal to the integral of cosine t dt. So t cubed y is equal to sine t plus some constant c. But remember that y of pi equals 0. But what does that mean? Here, we'll write this on the back. So when t equals pi, we know y has to be 0. We're going to use this information to solve for c. Now, remember we have t cubed y is equal to sine t plus c. And so I'm going to plug in my info. I'm going to get pi cubed times 0 is equal to sine of pi plus c. But the left side is 0, sine of pi is 0, and then we add c. And so therefore, c is 0. And so what that says is t cubed y is equal to sine t plus, well, in a sense, 0, right? And so y is going to be sine t divided by t to the third. And that would be the solution for example 2. Let's take a look at example 3. Suppose I had this one. Suppose I had x squared y prime plus 2xy is equal to natural log of x. Y of 1 is equal to 2. And so you're noticing in these examples, sometimes we need to do the integrating factor, sometimes we don't. If it's already written in the form of the product rule, we don't need to do the integrating factor. Now, what do I mean? Notice how the derivative of x squared is equal to 2x, and the derivative of y is y prime. So we're already perfectly set up. We could write this as the derivative of x squared times y. It's perfectly made for that. And then on the other side, we get natural log of x. So x squared times y is the integral of natural log of x dx. And so this is classic integration by parts. So I'm going to let u be natural log of x. dv is 1 dx. So du is 1 over x dx. And v is equal to x. So therefore, x squared y is equal to uv, which is x ln x, minus the integral of v du, which is x times 1 over x dx. So x squared y is x natural log of x minus the integral of 1 dx. So x squared y is x times natural log of x minus x plus c. Now, let's go back. Remember that y of 1 is equal to 2. So what that means is when x is 1, y equals 2. We're going to use that information to solve for c. So we get 1 squared times 2 is equal to, now x is 1, so we're going to take 1 times natural log of 1, we're going to subtract 1, and we're going to add c. So 2, natural log of 1 is 0, so we get 0 minus 1 plus c. But 0 minus 1 is negative 1. So 2 is negative 1 plus c. Therefore, c equals 3. And what that says is x squared y is x times natural log of x minus x, right, plus 3. And if I divide by x squared, I am done. I get x times natural log of x minus x plus 3 divided by x squared. And that right there would be the solution to example 3. Let's take a look at one more example for this video. Suppose I give you this one. Suppose I had, we'll do this one, x squared plus 1 y prime plus 3x times y minus 1 equals 0. Y of 0 equals 2. So you notice in the last several examples, we haven't had to utilize the integrating factor because it was already in the form of the product rule. Well, that's not going to be true in this example. We're going to need the integrating factor. And so we need to manipulate this a little bit. So we're going to write this as x squared plus 1 times y prime. Distribute the 3x in, and we get 3xy minus 3x equals 0. So x squared plus 1 y prime plus 3xy is equal to 3x. Divide both sides by x squared plus 1. And so y prime plus 3x over x squared plus 1 times y is equal to 3x divided by x squared plus 1. So now we're in position for the integrating factor. And so I of x is e to the integral of 3x over x squared plus 1 dx. Now, what I'm going to do, if you don't mind, is I'm going to take out the 3. So this is e to the 3 times the integral of x over x squared plus 1 dx. Now, I'm going to show you something off to the side here. So that way we don't have to do a u substitution. The integral of f prime of x divided by f of x dx. This is equal to natural log of the absolute value of f of x plus c. Okay? It could be easily verified by a u substitution. The derivative of x squared plus 1 is 2x. And so notice how we're missing a 2. So I'm going to put that in. But you can't just put in a 2 without dividing by 2. And so what I need to do is I need to multiply this integral by 3 over 2. And now I'm in perfect position. And so this is equal to e to the 3 halves natural log of the denominator, which is x squared plus 1. No c is needed, by the way. And I don't put absolute values around the x squared plus 1 because it's always non-negative. And so this is e to the natural log of x squared plus 1 to the 3 halves, which is x squared plus 1 to the 3 halves. So what I need to do is I need to multiply both sides by x squared plus 1 to the 3 halves. So I'm going to get x squared plus 1 to the 3 halves y prime plus 3x over x squared plus 1 times x squared plus 1 to the 3 halves times y. That's on the left side. On the right side, we're going to get 3x over x squared plus 1 and I'm going to multiply by x squared plus 1 to the 3 halves. Now, this looks interesting, but we can simplify this a little bit. So we're going to get x squared plus 1 to the 3 halves y prime plus 3x times x squared plus 1. 3 halves minus 1, right, is equal to a half. So I'm going to write 3x times x squared plus 1 to the half y. That's on the left side. On the right side, we get 3x times x squared plus 1 to the half. And so by design, notice how y, the derivative of that, is y prime. The derivative of x squared plus 1 to the 3 halves, by the chain rule, I claim is going to be 3x times x squared plus 1 to the half. Okay? So this is going to be the derivative of x squared plus 1 to the 3 halves times y. That's on the left side. On the right side, we get 3x times x squared plus 1 to the half. And so x squared plus 1 to the 3 halves times y is the integral of 3x times x squared plus 1 to the 1/2 dx. So let's rewrite that on the other page. So we get x squared plus 1 to the 3 halves times y is equal to the integral of 3x times x squared plus 1 to the 1/2 dx. If you want to do a u substitution, that's fine. I could let u be x squared plus 1. du is 2x dx. So x dx is 1/2 du. And if you want, we could multiply both sides by 3. So 3x dx is 3 over 2 du. And so therefore, x squared plus 1 to the 3 halves y is 3 halves times u to the half du. So x squared plus 1 to the 3 halves y is 3 halves times the antiderivative of u to the half is 2/3 u to the 3 halves, and then we add c. But remember that u is x squared plus 1. So x squared plus 1 to the 3 halves y is x squared plus 1 to the 3 halves plus c. Now, y of 0 is 2. So that says when x is 0, y is 2. Okay? So I'm going to plug that in. So I get 0 squared plus 1 to the 3 halves times 2 is 0 squared plus 1 to the 3 halves plus c. So 2 is equal to 1 plus c. So c is 1. Now, what that says is x squared plus 1 to the 3 halves times y is equal to x squared plus 1 to the 3 halves plus 1. And solving for y, I get 1 plus 1 over x squared plus 1 to the 3 halves. So that's a long problem. That'll conclude this video for section 9.5. We solved 4 initial value problems. Okay, thank you.